Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class, we reviewed some basics about the classification of PDEs. We looked at the PDEs and ODEs, heat equation, wave equation, Bondiler equation, and we basically saw how we can classify them as the homogeneous or non-homogeneous equation, linear or nonlinear equation, and so on and so forth, right. In today's class, we are going to basically discuss equations can be classified into elliptic, hyperbolic and parabolic equations. So, we will go into the definition of these hyperbolic, parabolic and elliptic equations later, but before that I want to say that this classification is very important from the perspective of the implementation in CFD. Unlike the classification whether the equations are PD or OD or it is a linear or non-linear, this particular discussion is important because it gives you the physical insights, okay, into the basically the dynamics, how the flow is evolving in time or in space, right. So, let us look at this classification and then we go to the physical interpretation of these equations. Right. So, before going there, so we are going keeping our discussion limited to the second order differential equation. Why the second order differential equation? Because our Navier-Stokes equation is a second order differential equation. Why it is second order? Because if you look at the equation, okay, and this term, okay, contains the, so this term contains the derivative, okay, and that you take the derivative again of that derivative. So, this is for example, in compressor flow it is exactly like this, del square u into nu, right, and even in the compressible side it will be like mu, okay, it will be 2 mu E I j, okay, del by del x j and minus 2 by 3 mu delta I j del u k by del x k, right. So, even in this case you have the double your order is basically del 2 by del x square or del 2 by del y square or del 2 by del z square, right. So, because of this term our Navier-Stokes equation is the second order equation, right. If you go to the Euler equation, this term drops out, okay, in that case you can call it as a first order equation, right. So, today we will look at a very general second order equation and then we will see how we can in certain limits we can see the character of the equation, okay. So, let us write a general equation. So, the general equation we have is, let me write it here, okay, we have A phi x x plus B phi x y plus C phi y y plus plus D phi x plus E phi y plus F phi and plus G equal to 0. As we have discussed earlier, the phi x x for example here means del 2 phi by del x square, okay. Phi x y will mean del 2 phi by del x del y, which is nothing but del 2 phi by del y del x, which is nothing but phi y x, okay, and so on and so forth, right. So, here x, y and y are basically independent variable. So, I am using x and y, but it can also be x and t for example, right, in certain situations, the time and the space also, or you can have two spatial directions. Okay. So, similarly, phi x will be del phi by del x. Okay. Now, as we have been discussing that whenever we try to look at the character of the equation, we will look at the highest derivative terms, highest order terms or highest derivative terms, right. So, here the highest derivative terms are basically a phi x x plus b phi x y plus c phi y y, right. So, we will club all those things together, okay, and we will focus on the highest derivative terms. Okay. So, this will become a phi x x plus b phi x y plus c phi y y and plus let us say call it h equal to 0, this entire term is equal to h, right. Now, we have these highest derivatives, right, highest order derivatives phi x x, phi x y, phi y y. Now, when we characterize this equation, we want to see what are the regions in the location. So, we want to solve this equation in a particular domain, right, in a particular let us say this is the domain where you want to solve the equation. We will provide let us say some boundary conditions here, okay, and some initial conditions, some for phi in the beginning, and we want to see that how that phi evolves in space, right. For example, here if it is x and y, right. Now, there could be situation where you may not get the exact derivative of this phi x x, or the derivatives either the derivatives are not defined or there may be multiple definitions. Okay. So, we want to look at those locations, okay, look at those lines along which these derivatives are not defined, undefined, or they can have multiple solutions, right. So, those lines are called the characteristic lines. Okay. So, we are looking for the regions where the highest order derivatives are undefined. Okay. So, how do we identify that? So, right now we have this a phi x x, b phi x y and c phi y y. We need we have basically if you write in the matrix form, okay, we have this phi x x, phi x y y and phi x y and phi y y. Okay. And right hand side let us say I put it minus h, and then we have this a, b and c, right. In order to basically get a meaningful solution to this matrix, we need two more expressions. So, what we will do, we will basically use the definition of the total derivative. Okay. We will call this just d phi x. How do we define d phi x? Okay. So, del 2 phi by del x square into dx, because it depends on phi depends on both x and y, remember that. Okay. So, del 2 phi by del x del y into dy, right. So, this is basically phi x x dx plus phi x y dy, okay, that will give you d phi x. And similarly, you can have d phi y will be phi x y dx plus phi y y dy, right. So, we got two more equations using these definitions. So, if you can use that, this is phi x x dx, this will become dx, phi x y dy. So, this will become dy, this will become 0, and this is your d phi x x, d phi x, right. And similarly, this is 0, this is phi x y. So, that will become dx, and this will become dy, will be d phi y, right. So, now we have a linear system of equations, right. We have 3 equations and 3 unknowns, okay, the phi x x, phi x y and phi y y, okay, and we want to find the solution for this phi x x, phi x y and phi y y. and we want to find the region where any or all of these derivatives are not defined, right. So, I am sure you must have gone through the linear algebra and solve this kind of linear system of equations, okay, where you do basically A x equal to b, right, where x is a vector, okay. It can have n number of elements, here it is 3, right. So, when you cannot get the solution of x, right, when, so if you want to get this solution of x, it will be A inverse b, right. So, when this A inverse is not defined, you cannot get the unique solution of x, right. And when is it is happening is when the determinant of A is equal to 0, okay, which means that either you can have the linear system of equations or you can have expressions. For example, let us say you can say that my expression is x plus y equal to 4, and then the second is 6x plus 6y equal to 37, right. So, if you try to solve this problem, you will not get a unique solution, okay. In fact, you will not get a solution, right, because if you write this in matrix form, this is 1 1 6 6 x y is equal to 4 37, okay. And if you take the matrix of this, the determinant of this becomes 0, right. So, using the same logic, if we are interested in finding the regions for which the solutions of this phi x x, phi x y and phi y y does not exist, what we need to do? We need to basically see where the determinant goes to 0, okay. And wherever that those determinant goes to 0, there the solution will either not exist or not defined, or you cannot find a unique solution, right. So, and those regions will be our characteristic lines, okay. So, let us look at the region where this is not defined, right. Yeah. So, look at the matrix that we have A, B, C, and then you have dx, dy 0, and then 0, dx and dy, right. And we want, if this is your x matrix, capital S X matrix, we want this determinant to be 0, right. So, get the determinant. So, how do you define the determinant? So, this is A dy square, I am writing the determinant of x, capital X, okay. So, A dy square minus b dx dy plus c dx square is equal to 0, right. That is the determinant of this matrix. Then it will be nothing. If I divide everywhere by dx square, this will become A dy by dx square minus b dy by dx, okay, and plus c equal to 0, right. Then solve this quadratic equation. So, your dy by dx will become b plus minus square root of b square minus 4 a c by 2 a, right, usual form, except that now we have this minus sign, that is why the minus disappears here, right. So, that quadratic equation, that equation that we have, remember the general form equation A phi x x plus b phi x y plus c phi y y is equal to minus h. This was our equation, right. We are looking for the characteristic lines for this equation, right, and we got this characteristic line. This is defined by dy by dx equal to b plus minus square root of b square minus 4 a c by 2 a, right. Now, when now look at in order to find out where the characteristic lines are present, we need to see whether the solution of this dy by dx is real or imaginary, okay. If it is real, then the solutions exist, okay. That means that you do not have characteristic line, but you have characteristic line, okay. And if you have the imaginary solution or this b square minus 4ac less than 0, okay, then you do not have characteristic line. Okay. So, let us look at this expression. If b square minus 4ac is less than 0, okay, that means you will not have the real solution, no real solution for dy by dx, okay, and this kind of equations are called the elliptic equations. Okay. The second condition could be b square minus 4ac is equal to 0, right. In this case you can have just one real solution, and this kind of equation is called the parabolic equation. Okay. In this case there will be just one characteristic, and if b square minus 4ac is greater than 0, okay, then we will have two real solutions. And these kind of equations can be classified under hyperbolic equations, okay, and it will support two characteristic lines, maybe two lines along which the discontinuities exist, or you may have the your derivatives cannot be defined, the highest order derivatives cannot be defined. Okay. Now, to make it more clear, let us look at some examples, some flows that we have already seen. Okay. So, first case is basically this is the Laplacian equation. Okay. You might have seen it in many different flows. Okay. For example, if you have studied the potential flow, okay, then the potential flow which is basically inviscid, irrotational, okay, in those kind of flows of course incompressible. Okay. So, you can basically use this your equation gets reduced to this Laplacian kind of form. Okay. So, we need to find out basically how this equation can be classified. Okay. So, if you write in this form a phi x x plus b phi x y plus c phi y y equal to minus h. So, if you compare this, this is phi x x, this is phi y y. So, your a is equal to 1, b is equal to 0 and c is equal to 1, right. So, your b square minus 4ac is equal to minus 4. So, this is less than 0. Okay. So, no characteristic, right. That means the derivatives are defined everywhere in the domain, right, and you will get only the smooth solution. Okay. So, let us say if you want to solve, so this can also be I mean this equation, if you write in let us say del square t equal to 0, okay, that is also the same equation. This is the steady state heat condition equation in 2 dimension, right. So, if you let us say you have a domain like this, okay, and you put some disturbance here in the beginning, okay, let us say you put a heat source here, let us say put a heater there, okay, and you may have some boundary conditions here. Okay. So, as soon as you put a heat source, okay, what will happen, because no region around this along which the characteristic is defined, right. So, there is basically no discontinuity, so it will smoothly go in every direction, okay, and it will only support the smooth solution, right, regardless of your boundary condition. Okay. Your boundary condition may be something here. So, you can have the temperature, let us say it can be 100 and other places can be let us say 50 and 30 and so on and so forth. Okay. Your boundary condition may have basically difference or inhomogeneity, but because it supports only the smooth solution, the solution within the domain will always be smooth in the case of elliptic equation. Further, like we have discussed earlier, that as soon as you put a point source or a heat source in this particular case, it will start basically radiating in all the directions, okay, basically propagating in all the directions, and that happens at an infinite speed. Okay. So, the effect of this heater will be felt immediately, ideally, okay, in the room or in this entire domain regardless of your boundary condition. Okay. So, if you want to solve this problem numerically, it is a bit hard problem to solve, because you know what will happen in this is that you need to create a grid where let us say if this is your source. So, this source would depend on the domain everywhere. Okay. So, this is the entire domain is your domain of influence, it is influencing everywhere. Okay. So, there are two terms, one is the domain of disturbance and domain of influence. So, here we have disturbed it here only maybe here, but because this is an elliptic problem. So, the domain of influence is everywhere. Okay. So, the value at this particular points depend on value of every single point that in the domain, okay, everywhere in the domain. Okay. So, you need to devise a scheme where if you want to calculate derivative at any point in this domain, it should be calculated using every other point in the domain ideally. Of course, it is not possible to include the entire stencil, okay, but ideally it should go with an infinite speed, and that is why the derivative calculation should be done considering every point in the domain. Okay. So, this kind of problem is also called the initial value problem. Why? Because you just perturb it initially, okay, just give some disturbance in the beginning, and it will be basically propagated everywhere in every direction. Okay. So, your domain of influence is everywhere. Okay. So, this is an initial value problem. Let us look at the other example, okay, which is basically the similar to the unsteady heat conduction that we already saw. So, this is like an unsteady heat conduction. Okay. Let us look at the nature of this problem. Okay. Go back to our expression A phi x x plus B phi x y plus C phi y y plus D is equal to 0. Remember, we need to only worry about the highest order derivative. So, we did not worry about the lower order derivative, which is del phi by del t here in basically characterization of the equation. Okay. And this is an one dimensional, this is 1D heat conduction, so we are considering only 1D, right. So, what is A? A is here K, okay. B 0, C 0, okay. So, B square minus 4 AC will become 0 minus 4 into K into 0, which is basically 0, right. So, your B square minus 4 is equal to 0, that means you will have one characteristic line. That means there is only one line across which the derivative phi x x is either not defined or basically cannot be determined. Okay. So, if you look at I mean physically if you look at this problem, so these kind of equations are called the parabolic equations. Okay. So, if you really look at this problem, okay, so what does it say that you are trying to basically find the solution of this equation using your in time. Okay. So, what you do, you put a disturbance at t equal to just t 0, okay, some disturbance you put, and then you see that how it basically how this initial disturbance is basically changing in time, right. So, what it says that whatever distance, whatever let us say you have a metal rod or something, and you put at one end you put a temperature gradient, right, or increase the temperature, and you see that how basically the temperature is getting distributed across the rod, right. So, once you put the disturbance here T equal to T 0, that is where your characteristic line exists, right. So, it cannot go anything past. So, it cannot basically influence what is negative in the time, but it will influence only what is positive in the time. Basically, this is T going greater than T 0. So, this is slightly difficult to interpret, because you know that anywhere time is positive, right. So, why we are discussing this, but this is an example of unstated condition. Let us say the example of the Bondiler equation that we have discussed, u del u by del x plus b del u by del y is equal to nu del to u by del y square, right. This is your Bondiler equation, right. So, in this case also you, if you work out, your A is equal to 0, B equal to 0 and C equal to nu, right. So, then again it will become B square minus 4 AC equal to 0. So, this is also a parabolic equation, right, but now there is no time here, but this is space, right. So, if you want to understand the parabolic equation, let us look at this Bondiler equation here, and this is how your Bondiler is developing. Okay, this is your delta, this is your L, right. So, what parabolic equation says that whatever is happening in the future depends on the immediate past. Okay. So, you cannot go, so you put a disturbance here somewhere here at the edge of the plate, okay, with let us say this is L equal to 0, but once you did that you forget about this. Okay. So, your domain of influence is always on the right side. Okay, is your domain of influence. So, it will only propagate in the rightward direction, right. So, left side does not know what is happening on the right, but right side is depending on the left side. So, that is what is your domain of influence, right. So, just like we said that what happens at T equal to T 1 or T 2 in the case of heat conduction depends on whatever disturbance you put at T equal to T 0. Similarly, in the Bondiler equation, so whatever you have happened that at the edge of Bondiler, that thing will propagate and that will decide how the Bondiler is going to basically form on the flat plate, right. So, your delta x you can determine based on the immediate past history or what was the length of the plate. Okay, so, that is what you mean by the parabolic equation, right. Now, look at the most interesting one, which is the hyperbolic equation, and as we have discussed earlier, this is the wave equation, and what I am going to do, I am going to write it in terms of x. So, now we have two independent variable which is x and t, but our expressions have been a phi x x plus b phi x y plus c phi y y plus h equal to 0, right. So, to make our life easy, okay, let us write it minus c square, let us say phi x x and plus phi t t equal to 0, right. And let us say my x is x and t is basically y here. So, then your a is minus c square, okay, b is 0 and c will be basically 1, right. So, your b square minus 4 a c is equal to 0 minus 4 into minus c square into 1, which is basically 4 c square. So, this is always going to be positive. So, you will have two real solutions, that means two characteristic lines. So, there are two lines at which the solutions are undefined for the highest order, right. So, this not only tells that, and these kind of equations are called the hyperbolic equations. Okay. So, this not only says that, it also actually provides you a mean to basically determine the solution of the equation, right. So, for example, if I want to write it like this, so this will be dt by dx will be b plus minus square root of b square minus 4ac by 2a. Remember, we have said t is basically equivalent to y in our this expression like this, right. So, b is 0 and this is plus minus square root of b square 0 minus b square minus 4ac is already 4c square we have obtained. Okay, so just write like that. Okay, this is 4c square root by 2 into minus c square, right. So, this is plus minus 2c by minus 2c square, this is plus minus 1 by c, right, or you can write dx by dt is equal to plus minus c. Okay. So, this we also got our characteristic line. Okay. So, the characteristic line will be along the direction which is basically dx by dt equal to c and dx by dt equal to minus c, right, in two directions. Like remember in the last class we discussed that when we speak something it goes with the c and minus c, the same thing we have basically got it from the discussion of the characteristic also. So, let us say if you want to solve this equation, okay, and let us say you have given the initial condition let us say u equal to 0 and del u by del t equal to 0 at t equal to 0, right. So, how do you get the solution? So, you can write it the solution as u, because you know that these are the characteristic line. Okay. So, you can write this f x minus c t and plus g, just let me see, x plus c t, right, because these are our characteristic lines. So, this is zeta, there are two characteristic lines zeta x minus c t and eta x plus c t. So, we can basically define our entire thing in terms of this characteristic line, okay, and then you can have some multiplying functions in this, right, and then you can define, okay, because u is equal to 0 at t equal to 0. So, that u 0 will become f x plus g x, okay. You can have some constant also here, and then this is u by dt t equal to 0 is also 0. This will become u prime 0 equal to, and then you put this is minus c f prime x plus c g prime x, right. These are the initial conditions that you have. You can use this initial condition and you have the differential equation this of this form, and you can solve it for an infinite domain. If you have a finite domain and you have some boundary conditions, you can use that boundary condition and you can get the solution. Remember, for the delta function we had basically discussed the solution. So, if you have an initial disturbance of some delta function, okay, we had the solution of half delta x minus c t and plus half delta x plus c t, right, for this particular equation. So, that can be determined by using the characteristics, the lines that we have obtained, right. So, the hyperbolic system is a very interesting system, and this will be very useful when you go to the high Mach number flows. Okay. So, the Navier-Stokes equation basically displays different behavior depending on what is the regime, right. Let us say if it is a very low Reynolds number and low Mach number flow, then it is more like an elliptic system, your viscous term dominates over the other term. On the other hand, if it is a very high Mach number flow, then it displays like a parabolic behavior, the behavior of the system is parabolic, right, where the advection system dominates. Okay. This looks like this is like an advection equation that we have discussed. So, I will conclude this with one final thought, that you can take a general expression, we can just confirm what we just said, and this will be a homework for you to go back and see. So, we are discussing about an inviscid isentropic compressible flow over a circular cylinder, okay, and we can like we have the potential flow, we can write an expression for this, which is given as 1 minus Mach infinity square del 2 phi by phi the velocity potential del 2 phi by del x square plus del 2 phi by del y square, right. And you please go back and use the derivations, the definitions that we have discussed, and so that if Mach is equal to 1, then you will have one real characteristic and it is like a parabolic system. Okay. So, when it is a sonic condition, it is like a parabolic system. When it is subsonic, Mach infinity less than 1, it is like an elliptic system, okay, for this particular case. And for Mach greater than 1, it will have two real characteristic and it will display a hyperbolic system, right. You can easily go back and show that. All you need to do is show what is A, what is B, what is C, determine B square minus 4AC, okay, and put different conditions of Mach number, okay, Mach infinity, and you can show this. Okay. So, this is a very useful classification of the PDEs into elliptic, parabolic and hyperbolic, and we will come to this again and again when we talk about the numerical schemes of solving the problem related to the advection, related to the diffusion and related to the advection diffusion both. Okay. With that thought, we will conclude the class today and we will meet in the next class. Thank you very much.